Hi everyone. This chapter is a continuation of chapter 6. We will be talking about a different type of reaction here, which is elimination of alkyl halides. For any extra reading material, you can refer to chapter 11 in the ebook. So with elimination, you are breaking two sigma bonds. So both sigma bonds are broken. This is the rule for elimination. You search for two sigma bonds, you break those two sigma bonds, and when you break the two sigma bonds, basically you're gonna form a pi bond. With elimination, you have to use a base, and we learned that bases are nucleophiles, with the exception of bulky bases that we will be talking about. But the idea here is that both bases and nucleophiles, they do have lone pairs, but the role for the base is different than the nucleophile. Bases take hydrogens. Nucleophiles, they do add to the electrophilic carbon. This is the difference between a base and a nucleophile. So in order for elimination to happen, normally the base, we know that bases take hydrogens. So the base is going to attack a hydrogen. Now, which hydrogen is the base going to attack? Not any hydrogen, it's a specific hydrogen. And the hydrogen that the base want to attack, it has to be an acidic hydrogen. So normally an acidic hydrogen is a hydrogen next to the partial positive charge carbon. So this carbon is a partial positive charge because your direction of polarization is basically towards the X, which is the halogen. So it's going to leave this carbon to be partial positive, and that partial positive is more electronegative than this sp3 hybridized carbon. So that carbon over here is partial positive. That is going to make this hydrogen acidic. So that hydrogen is partial positive hydrogen. So this means that the base is going to come and attack this hydrogen here. We're going to give this hydrogen a name. This hydrogen belongs basically to a beta carbon. We're going to name we're going to label the carbons. This carbon that is connected to a leaving group is called an alpha carbon. And the carbon next to it, adjacent carbon, so we have here, this is going to be a beta carbon over here. We do have another beta carbon over there. So all the carbons that are adjacent to the carbon leaving group, we're going to label them beta carbons. These two CH3s are the same. So these betas, I'm going to call them beta 1. And this is going to be a beta 2 over here. So basically you do have two types of beta hydrogens. But the idea here is that the base is going to come, take the beta hydrogen, form a double bond, and the halogen is going to leave. So in this case, notice I broke two sigma bonds and I made a pi bond. And this is going to be my elimination of product. Always elimination of product is an alkene product. It's a carbon double bond carbon plus of course the byproducts in there, which is the base taking the hydrogen and any extra leaving a group or leaving group in the solution. Please remember that charges have to balance each other. For every positive charge, there is a negative charge counter ion that balances it. Again, bases, they should have lone pairs. So this is a base, this is a potassium tertiary butoxide, it's a base. So base over here is going to come, it's going to take the beta hydrogen. So if this is the alpha carbon, that is going to be my beta carbon. So the beta carbon has a beta hydrogen, base comes, takes the beta hydrogen, form a double bond, and the bromine is going to leave, and I'm going to end up having my alkene. So notice your alkene is here between the alpha beta. This is where you form your double bond. Your double bond is basically between the alpha beta. So in other words, I am losing the alpha halogen and I am losing the beta hydrogen. So I'm losing here in this case HBr. This is another example of a base. Notice all of these bases here. This one, so this one over here, we've talked about it in substitution. At the end of the chapter, I will link substitution with elimination because this reaction here has a substitution of product also. So this is a secondary alkyl halide. This is going to be a base. So that base is going to come, it's going to take the beta hydrogen, it's going to form a double bond, and the halogen is going to leave. Notice where did I form my alkene? My alkene is between the alpha, beta carbon. This is where my alkene is. So over here, the process is really straightforward, and the reaction is called dehydrohalogenation because you are losing a hydrogen, so this is why it's a dehydro, and it's a halogenation in there, so you're losing both a hydrogen and a halogen. And the process is called beta elimination because it involves the elimination or the loss of the beta hydrogen. So this is why it's called the beta elimination in there. As I mentioned, always locate where your alpha carbon is. It is the carbon which is directly attached to the halogen, and all the carbons attached to the alpha carbon, these are the neighboring carbons. All of them, these will be labeled beta hydrogen, so or beta carbons. So if there are more than one beta carbon, you will end up having more than one alkene. There are different bases, and most of these bases we've talked about in earlier chapters. You should know their names by now. Normally, bases are strong whenever they have a negative charge. They are weak whenever they are neutral. All of these bases, they have one thing in common, which is the lone pair. So when they are present, this means that, and they act as a base, the base always takes a hydrogen. When these act as a nucleophile, the nucleophile adds to the partial positive carbon. There are two bulky bases in here, and these bulky bases are the potassium tertiary butoxide and the lithium diisopropylamide, which is abbreviated as LDA. Now, both of these bases can never ever act as a nucleophile because they are so bulky that they cannot add to the partial positive charged carbon. So with these act as bases only. So they act as bases only. They don't act as nucleophiles. This means that they just take the alpha or the beta hydrogen, the acidic hydrogen. With the others, since they are smaller bases, they act as both nucleophiles and bases. So whenever they are present, you have to consider them as nucleophiles, write their substitution product, and then consider them as bases and write their elimination product. Now we will be talking about linking substitution to elimination, but it's going to be at the end. But for now, let's go ahead and continue explaining elimination, the mechanism of elimination. So we will be treating those as bases only until we go ahead and explain both substitution and elimination together. So treating those with as a base, the first thing that you do whenever you want to write down the alkene product, which is the dehydrohalogenation product, the first thing you would do is you need to locate where is your alpha carbon. The alpha carbon is basically the carbon that is basically connected to the halogen. So this is going to be your alpha carbon in there. The moment you do your alpha carbon, you have to locate your beta carbons. And on these beta carbons, if there are hydrogens in there, then this is where the elimination is going to happen. Here in this example, I have two types of beta hydrogens. I have a beta hydrogen here, one of these CH3s, because both are the same. So we're going to label those over here to be basically beta, let me see, this is another example. So we're going to label those two to be pretty much beta 1, okay? And then on this carbon over here, this is a, oh, well, you know what? All of them are the same. So all of them are CH3s. This is a CH3, this is a CH3, and this is a CH3. So all of them are beta 1s. All of them. So I'm going to end up, if I have one beta hydrogen, then I'm going to end up having one alkene. If I have more than one beta hydrogen, as in this example, I'm going to end up having more than one alkene. So in here, the base is going to come take the beta hydrogen, form a double bond. So I'm going to end up having a double bond between these two carbons. This is going to be my first alkene product. Or if the base came and take this beta hydrogen in here, then I'm going to end up having my double bond between those two carbons, which is basically over here. You're going to end up getting two constitutional isomers. These two are called constitutional isomers. They are not stereoisomers because in here you do have cis and trans, but here there is no cis, no trans. So let's explain further the alkene, and it's just a revision on its hybridization and the bond angle. Remember that these two carbons are planar. This means that the bonds lie in the same plane and the bond angle is 120 degrees. With respect to alkenes, the carbons in the alkene, or the carbon in the ethane, they share basically a double bond where the two p orbitals overlap with each other. And when they overlap with each other, the pi bond is normally formed. When you look at alkenes are classified into mono-substituted, di, tri, and tetra-substituted. And this is basically based on how many R groups are attached to the alkene backbone. So you do have, this is the alkene. See how am I highlighting the alkene over here? So this is the alkene. To know which is which, to know your alkene and what type of alkene you are working with, highlight the alkene and see how many carbons it is connected to. So if it's connected to one carbon, then this means that it is a mono-substituted alkene. If it is connected to two carbons, it's a di-substituted. If it's connected to three carbons, then it is a tri-substituted. And if it's connected to four carbons, then it is a tetra-substituted alkene. So these are the types of alkenes that you will form during elimination. You will form any one of those. And you will be forced to pick the major product. So you have to know which one is going to be more stable, which one is going to be the least stable in there. So if I give you, for example, if you get this alkene, you have to know what type of alkene is that. So in order again to do this, the first thing that you would need to do is to just highlight the alkene part and then see how many carbons it's connected to. So here this alkene is connected to one carbon. We're going to call it mono. This is connected to two carbons because the rest are hydrogens. The rest are hydrogens. Here I do have two hydrogens over there and a hydrogen over here. Remember, every carbon has to have 4 bonds. Every carbon, 4 bonds. This alkene is connected to 3 carbons. This is a tri-substituted alkene. So with respect to stability of the alkene, alkenes normally are stable whenever you increase the number of electron donating groups on the carbon atom. If you take a look at the alkene structures in there, the different classifications of alkenes. If we consider the hybridization of each of these carbons, this is an sp2 hybridization for each of the carbon double bonds. And then since it's an R over here, then each of these R's is an sp3 hybridized carbon. Now, if you check the electronegativity, which one is more electronegative, you would see that the sp2 has more S character. So this means that it is going to be more electronegative. So if it is more electronegative, see how the direction of polarization is going over here. It is basically from the sp3 to the sp2, because sp2 is more electronegative. So your direction of polarization, this is the pull of electrons. Okay, now remember, we don't want the electrons to be centered in one area. We want the electrons basically to spread, the electronic cloud to spread throughout the whole structure, to be more stable, for the structure to be more stable. Now here in this case, each of these sp2 hybridized carbons is pulling the electrons. So see how the electronic map is spreading in there. It's not just focused on the sp2s, no, it's basically all over here. And we're gonna call the R's, because the electrons are being pulled from them going towards the sp2. We're gonna call these R's electron donating groups. They don't donate groups like willingly. No, they donate groups. They are forced to donate groups because they are connected to a more electronegative element in there. So they are forced to donate electrons. So this is why we call them electron donating groups. The rule says that the more electron donating groups you have around the alkene, basically the more stable is your structure. And the reason why the more stable is your structure, because your electron density now is basically spread over a larger surface area. So your electron deficiency is no longer focused on one area. No, it's spread throughout the whole structure in there. So having an alkene connected to one R is going to be less stable than an alkene connected to two R's, then three R's, then four R's in there. So this is the degree of stability of substituted alkenes. Increasing the number of R groups increases the stability of the alkene. And the reason why, because sp2 carbons, these are more able to accept electrons, electron density. What I mean by that, I mean by it that they are more electronegative. And sp3 hybridized carbons are more able to donate electron density. This means that they are less electronegative. There is a restricted there is a restricted rotation around the carbon double bond carbon. Now we've studied the conformation of carbon single bond carbons, and we said that you can freely rotate around the carbon single bond carbon, and we've seen this drawing the Newman projection staggered in eclipse. So you can do free rotation, but around the carbon double bond carbon you can't. The only way you can change basically from cis to a trans isomer is by breaking the double bond. Now we've considered in cycloalkanes the name cis and trans, and we said that cis and trans, they occur in cycles, and cis, whenever the substituents on the cycle, you need to have two substituents on the cycle, and the substituents can either be the same or they are different. It really doesn't matter, but they have to be two substituents. And these substituents, they can exist either as on the same side. If they are on the same side, it's cis, and if they are on opposite sides in there, whether they are adjacent, whether they are close to each other, it doesn't matter where they are on the ring, okay? As long as they are two, then you do have two stereoisomers in this case. One is going to be cis and the other one is going to be trans. There is no way, we said that there is no way you can rotate from cis to trans. This is why cis and trans are never mirror images of each other. This is in case we are talking about a chiral center. So if you're talking about a chiral center in there, then definitely the cis is going to have a mirror image to be cis. If you are not able to draw a plane of symmetry, here in this case I cannot draw a plane of symmetry. And by drawing a plane of symmetry, let me erase this one. So by drawing a plane of symmetry, that nope, Okay, by drawing a plane of symmetry that passes, here we go. So this is going to be the plane of symmetry that passes through this carbon over here. I can easily get mirror images throughout this plane of symmetry, so I would know that the cis exists as a meso compound. Okay, there is no chiral, there is basically no chirality in there. Even if you take a look in here, yeah, this carbon is different than this carbon over here because the connectivity is different. So you do have a chiral center over here. There is a chiral center here. There is a chiral center in here, but this molecule is not chiral, it's a meso compound because you are able to draw a plane of symmetry within the molecule. If I consider the trans, so if I consider the trans over here, so it's going to be the trans. Now, with respect to the trans, I cannot draw a plane of symmetry. So the trans exists as a pair of enantiomers. So the trans will have a mirror image in that case, and the mirror image will look like this. This is going to be the mirror image of the trans. Notice, mirror image of the trans is a trans. If cis had a mirror image, then it will be cis. You cannot go, this means, and it proves that, you cannot go from cis to trans by rotation. The difference between the enantiomers is simply the rotation around the chiral center. So you cannot go from cis to trans by rotation, and this is why we label cis and trans to be diastereoisomers whenever you have a chiral center. Now, if you don't have a chiral center, like in the case of alkenes, another case you can have cis and trans is whenever you have an alkene in there. So groups that are arranged around the carbon double bond carbon can either be on the same side, so this is the carbon double bond carbon. The groups can either be on the same side. Now notice here, I don't have any wedges and dashes because everything is in a plane. This is trigonal planar. So the CH3s can either be on the same side or they can be on opposite sides. If they are on the same side, normally I draw the skeletal like this, or I draw the skeletal structure like that. If they are on opposite sides, then the skeletal structure is drawn like this, or it is drawn like that, just showing that the CH3s are trans to each other. Cis and trans, normally they are stereoisomers of each other, and these, they cannot, they basically, you cannot go from one isomer to another by rotation, so you cannot interconvert by rotation. These are considered to be completely different molecules. Okay, they are stereoisomers. You do have a stereocenter in this case. There is a stereocenter, but there is no chiral center. So these two are not mirror images of each other. No chiral center, but they are stereoisomers in a form of cis and trans. Now, normally we don't call them diastereoisomers because there is no chiral center. To be able to call them diastereoisomers, normally we need to have a chiral center. Like in this case over here, we have chiral centers, so the cis and trans are diastereoisomers. Trans has its own mirror image, but these two, you don't have a chiral center in either one of those, so we don't call them diastereoisomers. These are called geometrical isomers. Cis and trans, geometrical isomers, and the carbon double bond carbon is a stereocenter. Stereocenter means that the groups around it exist as either on the same side or on opposite sides. So as you can see, there is no way for me to go from cis to trans unless I break the double bond. Now, if you have a molecular model, just go ahead and build the alkene, build the cis, and try to make it a trans. By rotation, you would see that there is no way. If you rotate it, no matter what degree you use, there is no way that you're going to go from cis to trans unless you break one of these bonds or you break the pi bond. Now, to connect the two carbons in the molecular model with each other, you have two sets of bonds. You have a longer flexible bonds, and you have a stiff bond. Use the longer flexible bonds and basically twist them in a way, and connect them to a carbon on one side and a carbon on the other side. And this is how you make the double bond. So the rule for cis and trans and alkenes, X and Y's normally they can be the same or they can be different. It really doesn't matter whenever they are on adjacent carbons. But if you have if you are working within the same carbon, X has to be different than X prime in order for cis and the trans to exist, and Y has to be different than Y prime in order for cis and trans to exist. So the two groups on each end of the carbon, double bond carbon, are different from each other, and if this is the case, then cis and trans exist. So let's say, for example, if I have something like this, okay, something like this, I have a CH3 here and I have a hydrogen there. So I'm fine on this side. These two are different, but I have a hydrogen here and a hydrogen there. I am not fine on this side. The two groups are the same. So in this structure, there is no cis, no trans. Okay? On the other side, I do have two groups over here. So I have two different groups on this side, hydrogen and CH3, and two different groups on this side, which is hydrogen and CH3. So this one exists as cis and trans. The way that I drew it right now, this is the trans isomer. The cis isomer, I have to draw it showing both groups. They are on the same side. Either they are pointing down or they are pointing up. Here, the trans, the CH3s can either one of them point up, down, or vice versa. One of them is up, the other one is down. So these two are going to be basically the isomers of each other. Stability of the trans alkenes. Always, if you want to compare, if you have different alkene products in your elimination reaction, and you ended up having a trans alkene and a cis alkene, which one is going to be more stable? Well, always remember this. The low energy one is going to be the most stable. For the cis, the CH3s here in this case, they are very close to each other. So see, there is basically repulsion in there between the CH3s. This is a steric interaction of both CH3s. It increases the energy of the structure. Increasing the energy of the structure decreases the stability. So cis is going to be less stable than the trans. The trans, the CH3s are completely 180 degrees away from each other. So they are going to be, it's going to be less energy because the CH3s don't interact with each other. So it's going to be more stable. So with respect to stability of the alkenes, always remember that a di-substituted alkene, this is a di-substituted, so this is your alkene, and you have two R groups on the alkene. If you have a di-substituted alkene can exist as either cis or trans. So if you have a di-substituted alkene, you have to write it as both cis and a trans. And when you write it as cis and trans, always remember that the trans is going to be the most stable. And then here I'm comparing it with the mono-substituted alkene. So definitely the di is going to be more stable and the trans is going to be the most stable in there. So in which alkene in each pair, is more stable? As we did, you go ahead and you highlight the alkene part and then check how many carbons it's connected to. So this guy over here is connected to one carbon. This guy is connected to two carbons over here. So see, I'm looking directly at the carbons that are adjacent to the alkene. This is going to be a di-substituted. This is going to be a mono. Then this one is going to be more stable. Same thing over here. I do have, this is my alkene, this is my alkene over there. Both are di substituted. So this one is a di substituted and this one is a di substituted. The reason why it's di, because see, next to the alkene you have two R's. Next to the alkene you have two R's, so you have di substituted alkenes. But one of the di substituted alkenes is cis, having the CH3s on the same side. The other one is trans, having the CH3s on opposite side. Definitely trans is more stable than the cis because the R groups are 180 degrees away from each other. These two over here, we're having a di substituted alkene, and with this one is also a di substituted alkene. Both have the same degree of substitution. So this is going to be a di substituted. This is going to be a di substituted. Now normally we prefer the R groups to be distributed between the two carbons. So this guy over here is going to be major product compared to this guy who's going to be minor product. And the reason why we want the R groups to be distributed around the sp2 hybridized carbons rather than just centered on one sp2 hybrid carbon. Over here you do have your alkene. This is your alkene, this is your alkene. So this is going to be a di substituted alkene. And this is going to be 1, 2, and 3. It's a tri-substituted alkene. So this guy is going to be major product. Label each pair of alkenes as constitutional, stereo, or identical. Again, in order for them to be stereoisomers, they have to be cis and trans because we don't have here a chiral center. So we're only talking about a stereo center, which is a cis and trans. So you locate your double bond and see the substituents around it. So here the substituents are opposite the same. So it's cis and trans. Same thing over here. Your substituent is opposite, your substituent is opposite, so we're going trans-trans. Now notice, if you're going cis-trans, then these are stereoisomers. Okay, cis-trans, these are stereoisomers of each other. Trans-trans, they are the same. They are the same in there. They are not stereoisomers of each other. They have to be the same. And as I mentioned, there is no mirror image in there, okay? So there's no mirror image to say that these two are enantiomers because there is no chiral center to start with. So no mirror image, no enantiomers in there. You're going from trans to another trans structure, so these two are going to be the same. Coming to A over here, you do have your alkene. This is going to be the these two are going to have different connectivity of atoms. They have the same molecular formula though, different connectivity of atoms, so they are constitutional isomers. Same thing over here. You can see that their molecular formulas are the same, but the connectivity of atoms is different, leading to a different structure. So we're going to call those again a constitutional isomers. Now, with respect to the mechanism of elimination, there are two types of elimination reactions. There's an E1 and there's an E2 mechanism. Both, normally, they happen simultaneously with SN1 and SN2. What I want to say in here is that the twos happen together. So if you have an E2, there is a possibility you have an SN2 with it. If you have an E1, there is a possibility you have an SN1 with it. You can never, ever, ever, ever have an E2 with SN1. You can never have E2 and E1 together. It's either or. So the ones happen together. So E1 happens with SN1. E2 might happen with SN2. Some reactions, conditions, they require only E2 as a product. They don't have SN2. And vice versa for the twos. But always with respect to the ones, whenever you have an E1, you're going to end up having an SN1 as a product. With respect to the mechanism of E1 elimination, E1 mechanism is basically a unimolecular elimination. It is a two-step elimination similar to SN1, but the mechanism is a little bit different because the product is an alkene in this case. It's not a substitution, it's an elimination. E2 is a bimolecular elimination. And there, the difference between E2 and E1 is in the type of the mechanism that we are working with and the number of steps. The number of steps that normally you go over in order to get your product in there. The twos happen together, the ones happen together. So let's consider the E2 first and then the SN2 and then the E1 reaction. So for the E2, as the basically the name suggests, it's a second order reaction. It happens very fast and normally it happens in one step reaction. This is why we call it a concerted reaction. There is no intermediate in there, so basically the rate depends on the concentration of the reactants. And the reactants are the concentration of the base and the concentration of the alkyl halide. So the rate depends on the concentration of the base, which is basically to the power 1, concentration of the, this is my base over here. This is my alkyl halide, which is to the power of 1. So the order of the reaction is going to be a second order reaction. The mechanism of the reaction is pretty much straightforward since it's a concerted reaction, which happens in one step. Now notice I've used a negative charge base, so this means that in this type of elimination, my base is a strong base. This is going to be a strong base. So that strong base is going to come, it's going to take the alpha hydrogen, it's going to take the beta hydrogen, and then it's going to form a double bond, and the leaving group is going to leave. Everything happens in one step. This is why we called it a concerted reaction. The breaking of the sigma bonds and the formation of the pi bonds happens simultaneously, together with the base taking the beta hydrogen to get the alkene in there. With respect to the energy diagram, since it's a one-step reaction, you pass from the reactants to the products. The products are stable, so this is why the energy of the reaction is going to be negative. This is delta H of the reaction, and delta H of the reaction is the enthalpy of the reaction, and it's basically negative, indicating that it is an exothermic reaction, since the energy of the product is way less than that of the reactants. So we say that this reaction is a favorable reaction and it proceeds with the direction written. Now, with respect to the speed of the reaction, you look at the activation energy and you measure it from the reactant to the transition state. To write the transition state, you have to show how bonds are broken. I am breaking here basically the bond between the carbon hydrogen, the bond between the carbon and the bromine. I am forming a bond between the oxygen of the base and the hydrogen, the beta hydrogen, and I'm forming a carbon double bond carbon or a pi bond. With respect to the condition of the reaction, as we did for substitution, we're going to also do the same thing for elimination, but with a little bit of tweak in there because E2 is different than SN2 by basically the type of the alkyl halide that you use. This is the only difference where E2 and SN2 parts from each other. So with respect to the E2, I'm still using a strong base. So the strong base is going to be any of the strong nucleophiles that I worked with before. So these are considered to be strong bases, OHs, ORs. Any base with a negative charge is considered to be a strong base. With respect to the leaving group, this follows also the SN2. So strong bases, they are same as strong nucleophiles. So if you have a strong nucleophile, then it will be a strong base, with the exception of bulky bases. Bulky bases, they act only as bases. With respect to the solvent is going to be polar aprotic solvent. I don't want the solvent to interfere with the strength of my base. I want my base to remain strong. So I don't want the solvent to solvate my base. So for the solvent to be completely inert to the base and doesn't react with it, my solvent has to be polar aprotic solvent. Polar aprotic solvent, they increase the rate of the elimination reaction. Now, with respect to the leaving groups, as we mentioned in there, we're still on the same idea. The weaker the base, the stronger is the leaving group, or the better is the leaving group. So I minus is a weaker base than a Br minus, because I minus comes from a strong acid, which is hydrogen iodide. And then it is basically, you do have over here the F minus. The F minus is a stronger base than the Cl minus, than the Br minus, than the I minus. So this is why F minus is a bad leaving group, because it is a stronger base compared to all of those. I minus is the weak base, and since it's a weak base because it's the conjugate base of the strong acid, then the I minus is going to be the best leaving group. Now this is where the alkyl halides here in this elimination conditions parts from the substitution. Remember when we said that with substitution, with SN2, SN2 happens faster when you have a methyl halide compared to primary alkyl halide, secondary, tertiary. There is no SN2 in there, no SN2. Now with elimination, no. With elimination, the rate of the reaction increases when the degree of substitution around the alkyl halide increases. So with elimination, we always in SN2 and in E2 and in E1, we're always want to have a tertiary alkyl halide. We always want to have a tertiary alkyl halide for our elimination product, always. So tertiary alkyl halides react faster than secondary alkyl halides, than primary alkyl halides with E2 reaction. Primary alkyl halides and methyl halides have no reaction in there. Okay, so I was writing this as an SN2, but with E2 you need 2 carbons to make a double bond, and the primary alkyl halide has only 1 carbon, so you don't need this option in here. You don't need it whenever you are working with E2 reaction. Always start from the primary. Primary is less stable than secondary, then tertiary, so tertiary is the fastest with E2 product. Now with bulky bases like potassium tertiary butoxide, like lithium diisopropylamide, potassium tertiary butoxide, normally you're gonna see me drawing it like a skeletal form, like that. This is how we draw the potassium tertiary butoxide over there. This is a very bulky base, and that base is hindered. It's electron pairs. See those electron pairs? These are hindered by the bulky carbons. So it's going to prevent that base to act as a nucleophile. So this can never add to make an SN2 product, but it will take an extra hydrogen. It will take an acidic hydrogen, because hydrogens are small, and that these lone pairs can take the acidic hydrogen, but they cannot add to the partial positive carbon in order to do a substitution product. In general, E2 happens with a secondary alkyl halide. It happens with a tertiary alkyl halide with any of the small bases. So with these two plus a small base. So what are the small bases? The small bases are OHs, they are ORs, and there, whether the R is 1 carbon, 2 carbon, 3 carbon, these are all considered to be small bases. And these small bases, they are strong if they have a negative charge. So the moment you see that they have a negative charge, this means that they are strong, then the mechanism is going to be an E2 mechanism. E2 on the other hand can also happen with primary alkyl halide, but in that case only, in that case I would need a bulky group in order to push the reaction to completion. So I would need to use a bulky base. If I use any small bases with the primary alkyl halide, I will end up having no reaction, no E2 reaction. So with primary alkyl halide, the only way the reaction can work is whenever I have a bulky base taking the beta hydrogen of the primary alkyl halide. Now, of course, secondary and tertiary alkyl halides, they go with the small bases or bulky bases, it doesn't matter. But the bulky basis is just a push for us to go towards elimination of product, because bulky bases, they don't have any substitution of product. So if you wish to carry a reaction where you don't want to contaminate your alkene product with the substitution product, then you would carry it with a bulky base. In that case, you ensure that your product is just the elimination of product and it is not the substitution of product because of the bulky base. Examples of strong bulky bases. So with a primary alkyl halide, you need to use a bulky base to have a reaction. So let's say if I use that primary alkyl halide and I'm reacting it with sodium hydroxide, this is a strong small base. So it will end up having no reaction, no E2 reaction. There is no E2 reaction in there. With potassium tertiary butoxide, since this one is a primary alkyl halide, then the base is going to come. The base is going to take the beta hydrogen. It's going to form a double bond and the chlorine is going to leave. Let me write down the mechanism of the reaction in there. So you do have the CH3. This is a CH2. This is 15 times. And then another H2. And then you do have your CH3 and the Cl, and you're using potassium tertiary butoxide. So you're using this one over here. Don't forget your lone pairs. So we're going to start by the base. The base is going to come. So that is my chlorine. The base is going to come. This is going to be my alpha carbon. This is going to be my beta carbon. So I know that the base is going to come, take that beta hydrogen, is going to form a double bond, and basically my chlorine, my halogen is going to leave. So I'm going to end up having a terminal alkene. The alkene is at the end. We call it a terminal alkene between the CH and the CH2. Notice when I change this into this structure over here to draw the mechanism, I detailed it. So instead of showing the beta carbon to be CH2, I simply took one hydrogen out, and just to show that the base is going to come take this hydrogen, I revealed the sigma bond between the carbon and the hydrogen, showing again that the sigma bond can be broken and form a double bond in there, and then the halogen is going to leave. Remember, if you keep the halogen, then the carbon is going to have 5 bonds, and this is chemically not possible. This is another example of a primary alkyl halide. So the moment you have a primary alkyl halide with E2 product, so here I'm going to have an E2 product, here I'm going to have an E2 product in there. So if you with an E2 product with a bulky base, then I would know that that guy over here, its only role is to take the acidic hydrogen, and not any acidic hydrogen, is one of the beta hydrogens. This is going to be the acidic hydrogen, not any of those, it's just one only. So I'm just going to go ahead and write 2 hydrogens over there. So now my base is going to come, it's going to take that beta hydrogen, it's going to form a double bond, and the halogen is going to leave, and we will get our alkene product. For secondary and tertiary alkyl halides, any strong base can be used, whether it's bulky or whether it's a small base, it really doesn't matter, it can be used. Conditions of the reaction: solvent is going to be polar aprotic solvent so that the mechanism happens faster. And if you wish to have an elimination as a product, you always require to have heat. Now, heat can be room temperature and above. This is what heat is. So if you see the temperature to be probably 22, 23, that is a room temperature in there. And elimination for some of the cases is very exothermic, and it is a fast reaction. So basically, all what you're having here is that base comes, it's attacking the beta hydrogen. So this is going to be the alpha carbon. One of these hydrogens, notice this is a hydrogen and this is a hydrogen. This is going to be beta. Now on the other side, since I can draw a plane of symmetry passing through the chlorine, this hydrogen is the same as this one over here. So that is going to be beta 1, that is going to be beta 2, and these two are going to be the same. So the base, it's going to come, it's going to take the beta 2 hydrogen, it's going to form a double bond, and the halogen is going to leave. On the other end, for this beta 1, the base is going to come, it can take this hydrogen, form a double bond, and the halogen is going to leave. Now, one thing that I want to say over here, both beta 1 and beta 2 are the same. The reason why they are the same, because the connectivities of the carbons are the same. So whether you draw it like this or this, I did this for a reason, just to show you that it is the same, or drawing the alkene like that. Here I'm labeling this, or I can start numbering the alkene from this carbon. Here I'm starting to number the alkene from this carbon. So it really doesn't matter, or I can number the alkene from basically this carbon over here, going by 1, 2. 1, 2, 3, 4. Here 1, 2, 3, 4. Notice when I number the alkene, I need to pass through all the carbons of the alkene. So going 1, 2, not 1, 2 like that. No, 1, 2, because I have to pass by the carbons of the alkenes in there. With respect to the solvents have to be polar aprotic solvent in order for the reaction to happen fast. Now, this doesn't mean that I cannot use polar protic solvents. No, I can use polar protic solvents in SN and E2 mechanism. But the thing is, if I use polar protic solvents, the rate of the reaction is going to decrease. So it's not going to increase, it is going to decrease by a bit, but not by too much though. So the reaction will be slower. The E2 reaction will be slower if I use a polar protic solvent. The effect of the leaving group in there, as we said, that the weaker the base, the better is the leaving group. And because the bond to the leaving group is partially broken in the transition state, the better the leaving group, the faster is the E2 reaction. So if I am comparing here between these different types of alkyl halides having the same carbons in there, definitely I would know that the alkyl halide that has an iodine as a leaving group, that is gonna be way more basically faster. That alkyl halide is gonna be faster than or proceeds faster in the reaction than the alkyl bromide, than the alkyl chloride, than the alkyl fluoride. Now, SN2 and E2 reactions, they do happen together. And there's a big difference between SN2 and E2. The difference is the type of the alkyl halide, as we mentioned before. So with the SN2 reactions, the reaction happens faster with the methyl primary, but and the secondary, but not tertiary. But with respect to E2 mechanisms, see, as you can see, they are opposite. The reaction is going to happen faster with the tertiary alkyl halide. For the transition state of the mechanism, The transition state has to lead to the most stable product. So if you have different types of beta hydrogens, each one is going to have its own transition state. Let me have an example over here. So in this type of example, in this example over here, I do have basically two, no, actually I do have one type of beta hydrogen in there. And here I do have another type of beta hydrogen here. So I do have basically one type of beta hydrogen. This is going to be my alpha carbon. This is going to be my beta hydrogen. So that is going to be beta, that is going to be beta, that is going to be beta, and all of those are CH3s. This is CH3, CH3, CH3. So my product is going to be just one product here. Same thing. This is an alpha carbon with a leaving group. The only adjacent carbon to it is this carbon. So I only have one type of beta carbon. This is not. These two hydrogens are not beta hydrogens. Why? Because these two hydrogens are not attached to an adjacent beta carbon. They are attached directly to the alpha carbon, so they are not. These two are not considered to be acidic or as acidic as this beta hydrogen over here. So here I have only one type of beta hydrogen. So the base is going to come take the beta hydrogen, form a double bond, and the bromine is going to leave. If I do this, then I'm going to end up over here having my alkene, see, and in this case, see my alkene here. My alkene is going to be a monosubstituted alkene. A monosubstituted alkene is an alkene that is less stable than a disubstituted alkene. Just comparing between a di and a disubstituted and a monosubstituted alkene, this guy over here is going to be more stable product. Now, normally the stability of the alkene has to do with the stability of the transition state. So if the transition state is stable, then the alkene is stable. If the transition state is not stable, then the alkene is not stable. And normally with respect to the transition state, the transition state is kind of like an alkene-like. And if it is an alkene-like, then you have to treat it like an alkene or as an alkene. I'll give an example over here in a second. So in order to check if you have more than one beta carbon, then you're going to end up having more than one alkene product. So the question is, based on their transition state, which one is going to be more stable? Or, in other words, which one is going to be the major product, which one is going to be the minor product? The rule says that the most substituted alkene is the major product, and the least substituted alkene is going to be the minor product. So all what you can do is just allow the base to take the beta hydrogens, form your alkene. Here I have two beta carbons, so two beta hydrogens. This is going to be a hydrogen over here. This is my first beta hydrogen. This is the beta 2. So the base is going to come, take that beta hydrogen, and it's going to come basically an attack from its lone pairs. Take the beta hydrogen, form a double bond, iodine is going to leave. This is the first double bond in here between these two carbons, which is over here. And if I want to look at the degree of substitution, this is going to be my alkene. And my alkene here, it is basically, it's connected to two carbons, so it is going to be a disubstituted alkene. Or I can do this. I can basically use this beta hydrogen and have my base come, take the beta hydrogen, form a double bond, iodine leaves, so my double bond is going to be in this area over here. And to determine the degree of substitution, highlight your alkene and see how many carbons are there in the alkene, and you have 3 carbons, so it's a tri-substituted. Definitely the more substituted the alkene is, the major it is. With respect to the regioselectivity of the E2, as we said, what determines the majority of the product, or what determines if the product is major or not, is the transition state. So if the transition state is stable, then the product is stable. If the transition state is not stable, the product is not stable. Here I am considering the case where that is this another example. I'm considering the case where you have two different beta hydrogens. So you're going to end up having two different alkenes as the product. Now, before leading to these alkenes as the product, you pass by the transition state, where the base tries to take the beta hydrogen, form a double bond, the bromine, leave. So these transition states, like they act like an alkene. So it's kind of like an alkene. This is your alkene in there. It's gonna later on change into alkene, but right now it's an alkene like. Okay, so if it's an alkene like, I know that the more R groups around the carbon double bond carbon, the more they donate electrons to that carbon double bond carbon and make it more stable. So here I do have a disubstituted alkane like transition state. Here I have, see how many? I do have 3. It's a tri-substituted. All of these 3 R's, they are donating electrons to the double bond. So this is going to be 3. This is going to be a tri-substituted. So the transition state here is more stable, and this is why it leads to a more stable major product. So the idea is always your major product is going to be the most substituted alkene. If you have more than one beta hydrogen, write all the products down, but then when you want to arrange them, just make sure you pick the major alkene, and that is going to be your major product. Now, the thing with E2 elimination, in this reaction, it's both. It is regioselective, it is stereoselective. Now, regioselective means that I have more than one alkene, and I would choose the major one based on the degree of substituents around the alkene. This is what a regioselective is. So a regioselective reaction is a reaction where the product normally is predominantly the major product. You have more than one product and you choose a major product, and that will be your high percentage of product. This is what a regioselective is. Now, what is a stereoselective? Remember that we are making an alkene, and if you're making an alkene, there's a possibility you make a cis and trans isomers in there. Now, this one has no cis and trans because these two are the same. This one has no cis and trans because these two are the same. But there are cases where, like for example here, I am using a strong base. So that strong base, let's see if we have acetone as a solvent. So if we have acetone as a solvent, this is a strong base in there. I know that this is strong base, and let's say we have heat. The base is gonna take this beta hydrogen, it's gonna form a double bond, and the bromine is gonna leave. So I'm gonna end up having my only double bond form is between those two carbons. So this is gonna be my double bond in there. Now, since around this double bond, I do have groups that are, so I have on this carbon, I have hydrogen and the benzene. These two are different. And on this carbon, I have a hydrogen and a benzene. They are different. So there is a possibility of two stereoisomers, which is the trans and the cis. Always the trans is more stable because you don't have steric interactions between the benzene groups. Now, when we say trans and cis in here, the reason why I base this to be a trans, because the substituents that basically are the same, they are on opposite sides of each other. You can either consider the phenyl substituents or you can consider the hydrogen substituents. You have to pick whenever you work with cis and trans, you have to pick substituents that are the same and see their orientation with respect to each other. I could have gone with hydrogens and say that these two hydrogens are opposite to each other, then this is trans. These two hydrogens are cis to each other, then this is going to be basically, or on the same side, then this is going to be a cis alkene.